Hi everybody, Mary here, and we're going to do another latent heat problem. And here goes. When I retire, I plan on making my fortune by publishing the world's famous ice cube diet. Eat anything you want, just add ice cubes. Now, the idea, of course, is because of the fact that you have to input heat, you have to input calories in order to melt ice, it's going to burn calories. So if each ice cube is 3 centimeters on a side, and they start out in a real typical refrigerator freezer that is minus 18 degrees Celsius, if I want to lose just 1 pound of fat, how many ice cubes would I have to eat? Now, 1 pound of fat means 3,500 kilocalories. So how are we going to figure this out? Well, we're going to go back to that latent heat graph. And as you recall, it looks something like this. And let's think about this. If I start out with little ice cubes, what changes are going to go through the heat of those cubes as I eat them? Well, my cubes are going to start out at minus 18 degrees Celsius in a solid form. We're going to have to warm those cubes up, and that's going to take some energy up to 0 degrees Celsius. And when we warm that ice up, we're in a situation where we're going to use the equation Q is mc delta T, because we're changing the internal kinetic energy of those ice cubes. Then we're going to have to melt the ice. Well, in the melting ice portion, I'm going to use latent heat of fusion. And I'm going to have to involve that to determine how much heat energy is absorbed to actually warm the ice cubes up to liquid water. And then I'm not going to stop there. I'm going to go up to body temperature, which is right around 37 degrees Celsius. And then I'm going to take some heat to warm that liquid water up to body temp. And because I am in this fraction of a graph, again, mc delta T. So my equation's going to look like this. I have 3,500 kilocalories, and you and I both know 3,500 kilocalories is going to be 3.5 times 10 to the 6th calories. 3 for 1, 2, 3, and then the other 3 for kilo. So 3 plus another 3 is 6, and that's where I get that power of 6. And the heat is going to be taken from these 1, 2, 3 locations. So I am going to spend that heat warming the ice, melting the ice, and then warming the water that used to be ice. And the question is, what's the mass? How much ice am I going to actually have to eat? So to warm the ice, this is going to be mc delta T, but this is going to be the mass of the ice, specific heat, not of water, but of ice, change in temperature of the ice, plus mass of ice, latent heat of fusion, because I'm in this fraction of the graph, and then warming the water that used to be ice. Warming the water. I wrote down, what the heck did I write down? Let's write down warming water. So we're going to be in this fraction of the graph up here, warming the water from 0 up to 37, the mass of the water, specific heat now of water, and change in temp of water. Now I'm going to do this problem in calories. You could also do it in joules. Doesn't really matter, but I'm going to do it in calories because I'm kind of lazy and it's going to be a smidge simpler. So 3.5 times 10 to the 6th calories. M is the mass. That's what I'm looking for. The specific heat of ice in calories is 0.5 calories per gram. The change in temp is going to be from minus 18 up to 0, because when it gets to 0, it stops being ice, and now it's going to be an ice-water mixture. So the change in temp of just the ice is 18 degrees Celsius. Plus mass, latent heat of fusion for water is 80 calories per gram. Now, where am I getting these numbers? Well, you can look them up on your physics constant sheet, or of course you can always look things up online. The mass of the ice, specific heat of water in calories is 1 calorie per gram degree Celsius, And what's the change in temperature? Well, the change in temperature for the water is going to be from that 0 up to 37, because here it's liquid water. So the change in temperature here is 37 degrees Celsius. Okay, now let's do some math. Half of 18 is 9, so this is going to be mass times 9 calories per gram. That's actually a degree Celsius. I forgot that, and that will cancel. Plus mass times 80 calories per gram. And 1 times 37 times mass is going to be mass times 37 calories per gram. And degrees Celsius again will cancel. These have like terms. They all are multiplied by mass, so I can just add them. When I add them all together, I end up with 126 calories per gram. Pull this down, 3.5 times 10 to the 6th calories. And this is all going to be times mass. So the mass of ice I need to eat is 3.5 times 10 to the 6th calories divided by 126 calories per gram, and that's going to give me 27,778 grams of ice. Now the question was not how many grams of ice, the question was how many ice cubes. Well, we were told that one of these ice cubes is 3 centimeters on a side. 3 centimeters high, 3 centimeters wide, 3 centimeters deep. So the volume of one cube is going to be 3 times 3 times 3, which is 27 cubic centimeters. Well, 27 cubic centimeters is the same as 27 milliliters. And for water, 1 milliliter is exactly the same as 1 gram. For ice, it's slightly different, but we're ballparking things here. So I'm going to go with the fact that there's going to be 27 grams per ice cube. So how many ice cubes am I going to have to actually eat? Well, just to make the math easy, let's round this off. If I've got 27,000 grams and I've got 27 grams per cube, if I do the math, that means I'm going to have to eat 10,000 ice cubes above and beyond anything else I eat or do just to lose a pound of fat. And we're not talking tiny little wimpy ice cubes here. 3 centimeters on a side, that is over an inch on each side. So this is a good solid hunk of ice here. Would I recommend this diet? It wouldn't be fast. It would take a while for you to do that. And it might hurt your teeth, but you'd burn calories. All right, guys, see you later.